a teeter-totter?
Let's talk about that.
Da 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 da.
Hey guys, today we're going to be doing a project on torque. Now, an example of torque would be like a wrench, like when you have like a nut and or a bolt, and then you use your wrench to tighten the bolt. Now, another example would be a teeter-totter. Both kids or grown-ups, it's a cool thing you can do if you want, can be on the teeter-totter, both have a torque exerted on the teeter-totter.
And the rotational equilibrium is achieved when the torques are equal and they therefore balance.
The equation to find torque is torque equals the force perpendicular, like pulling on a wrench or sitting on a seesaw, times the length of the lever arm, the length of your seesaw, or
the wrench.
Wrench.
Yes.
So what we're going to do with this project is we're going to take two different weights, which will be 8.90 newtons and 22.24 newtons, which are about 2 pounds and 5 pounds. We're going to use the math with that equation to figure out where we're going to have to put the 5-pound weight in order to achieve rotational equilibrium, which is, balance. Okay, so we have on our teeter-totter right now a 2-pound weight, which is, 8.90 newtons, approximately 1.09 meters away from the fulcrum, which is at the middle of the board. So we are going to use this equation to figure out where to put a 5-pound weight on that same board on the other side of the fulcrum to achieve rotational equilibrium, which is balance.
So the torque for the 2-pound weight on that length of the teeter-totter equals 9.7 Newton meters. And how we got that was I multiplied the weight times the how far away it is from the fulcrum. Now I need to figure out where to put the 5-pound weight on the other side. So to achieve rotational equilibrium, we already know the torque, which is the torque we got from our 2-pound weight. And that's going to equal the weight of the 5-pound weight, which is 22.24 newtons times the length of the lever arm, which we need to figure out. So in order to do that, we're going to rearrange the equation. So we have length of the lever arm equals the torque over the weight, and we get 0.44 meters, which is roughly 17 inches. So let's go to our science sector and see if it balances.
Okay guys, so we have our teeter-totter right here with our 2-pound weight, which is, 8.90 newtons, approximately 1.09 meters away from the fulcrum. Now Ian will measure out 0.44 meters, or like 17 inches, and that's where he will put his 5-pound weight, which is 22.24 newtons, and we will figure out, or try to achieve rotational equilibrium. As you can see, it's not achieving rotational equilibrium yet, even though it's precisely 17 inches or 0.44 meters away from the fulcrum. Well, that's because of something called experimental error. When we made this board, it wasn't completely balanced. As you can see, we have this book taped right here to try to compensate, and even then it wasn't perfect. Also, when we converted our inches to meters, we didn't use the complete number. We rounded to the hundredths place.
Yeah.
So Ian will try his hardest to, what we're trying to do now is get as close to rotational equilibrium as possible. Even though we don't technically achieve complete rotational equilibrium, the math is still proven.
Yeah. Oh yeah! Okay, so right now we have a 10-pound weight out there, which is the 22.24 Newton weight out there, and it is approximately 10 inches, which is 0.254 meters, and now Drew's going to figure out the torque of that.
After plugging everything necessary into our equation, we found that the 5-pound weight has a torque of 5.56 Newton meters. And then after plugging in a bunch of all the other necessary stuff into the same equation, we found that we have to place the 2-pound weight approximately 0.625 meters away from the fulcrum,
which is 24.61 inches. Let's go to the teeter-totter. So here we are at the teeter-totter. We've got the 5-pound weight right here, and Drew, you gotta measure it and see where to put the 2-pound weight. Got that?
Yep.
The weight.
Oh my gosh.
Rotational equilibrium.
Oh, dude.
So Drew, what did you learn today?
Well, Ian, I learned that teeter-totters are more complicated than they should be.
Every time we have something that's